Okay, so the next thing to talk about is the transfer formula. Now, if we want to get the moment of inertia around a non-centroidal axis, that means an axis that doesn't go through its centroid. Those original equations only work for that. Then we have to use this transfer formula, which is also known as the parallel axis theorem. It's a very simple equation. It's just adding a correction term, saying, well, all those equations we had, they were for these two axes, but now I'm spinning around these two axes. And like I said earlier, if you have a shape on the end of a very long bar, it becomes much harder to turn if you're at least going around this axis. And so very, very similarly, you'll see that the moment of inertia will increase as we move away from our central axis. So here it is. This is our initial moment of inertia. That's what we calculate using the formulas you're going to find in Table 3 in your textbook. And then we have this correction term, which is simply saying, okay, this is the distance between my centroidal axis and this new axis that I'm rotating around. That's that distance right there, d. And so this is very, very similar to the moment of inertia equation. And so you're just adding that in there to help correct it. And once you've done that, all is well, and you prosper. And if you have a composite area like made of multiple different shapes, you can just sum them all. So it's very, very simple in that regard. Now, how about a moment of inertia for a composite area? Now, here's the steps, and I'm going to show you this in an example fairly soon. But just write these down, or just make sure you know where this is. Just like before, we're going to be making a table. The table is like one of my favorite methods of doing this, and you'll be doing whichever axis you need. So y here, area, then you have your y squared a, and then you'll have d squared a. All of that, you'll get all those rows, or all those columns set up, put all your values in, and then you just add to the bottom and plug it into your equations. And it works very, very well. I've always found it the easiest way to solve these problems. And I try to show you the easy way, for most things at least. So, when you get stuck, follow these steps. First step, divide your composite area into common, simple geometric shapes, okay? Figure out where your centroid is for that composite area. Yes, you're going to have to do the centroid thing. You can't forget that. But we had an easy time of it, it seemed like. Chapter 7 wasn't too bad. Then you're going to determine the transfer distance from the centroidal axis to the composite area, okay? To the central axis of each of the component areas. So once again, all these centroidal axes and centroidal locations for these various basic shapes, you got to remember that even though, yes, you know that for two boxes it's right at the center, it's saying, okay, this is going to have some composite centroid, which would be like right here. That's the big centroid. And you want to know the distance from that point to everything else. That's your reference. Like, that's your origin now. Okay? And that's where you're going to get D for each of these. And you're going to compute the moment of inertia for each of these. And then finally, add them all together. Now, a more strange example right here is of the radius of gyration, which is really helpful in Chapter 18, which we're actually not going to get to this semester. But if you want to, you can look at it for reference. The big thing it's going to talk about is that the bigger this is, the larger a load a column can carry before buckling. Now, buckling we haven't gotten to, we're not going to get that for this semester, but it's simply a load where the column is fine, like, mechanically, like the metal or the wood or whatever is not going to break. But just because of the instability of the structure, when you put that load on there, it's going to literally bend in half. Now, it won't reach that point because it's going to break far long before it gets there, but that's what buckling failure is. The material itself is fine, but it begins to deform and bend because it gets just slight variations, slight imperfections cause it to bend one way or the other, and it can't stop itself. It's just not stable. So that's what the radius of gyration gets to. And in this case, it's just going to be a square root of our moment of inertia over the area of our cross section. Okay? Moment of inertia over the area of our cross section. Okay, and finally, one more thing, the polar moment of inertia, which I'll go ahead and show it to you here. It's simply the sum of moment of inertia around the x-axis and the y-axis. You just add them together. Or if you have this, you can do sum all the r squared a, which r is simply the distance from our centroid to wherever that is, not caring about the x or y direction. You can see them right here. Got a nice little right triangle. One side is y, the other side is x. This is our distance r. You see this a lot with circular cross sections, where there is no pretty like x and y direction. It's just like, well, it's a circle, so I could choose anything as my x or y direction. So in those cases, we would usually use the polar moment of inertia. Same thing for ellipse. That one has a little bit better x and y axis, but circles most definitely. Okay, so I believe, yes, that is everything for this chapter. So next time we're going to jump into a bunch of example problems, and we'll see you all then. So thank you for listening. I'll see you all soon. Bye-bye.